Moving ahead a little bit, we're looking into chapter or unit 3, and we're looking at light. Light is just one bit of energy on a whole spectrum of energies that range all the way from one side, radio waves, to all the way on the other side, gamma rays. And they are all related. The only difference is how large the wavelength is for each of those values. And consequently, as I change the wavelength, I change the frequency, how often you're hit. And if we know either the frequency or the wavelength, we can calculate the energy of each one of those waves, energy waves hitting us. Now, the energy of one of these waves, and that's what we're calculating, one in terms of light, photons, or in terms of heat, quanta, but remember, infrared energy heat and photon energy light are exactly the same thing. We just discovered them by looking at two different things, and that's why we have two different names, but they're all the same type of energy. Okay? We can actually calculate the energy of one of them hitting you, but we never get hit by one, we get hit by lots of them, and so energy can be transferred. Now, we can only detect visible light. Okay, our eyes can only perceive visible light, but we have instruments that can perceive or read all of the wavelengths that are available in all of the spectrum. But looking at the light really gave us some information that helped us understand what the structure is of the atom. Now remember, the atom takes up a sphere space, and we said electrons were buzzing around and the nucleus was very, very tiny with all the mass. But we didn't, at this moment in time, we didn't identify where those electrons lived other than in this big volume of space. But some of the experiments with looking at light and transitioning is going to give us an idea about where those electrons actually live inside that big space. They are actually organized. All right. So here is a picture of what we saw a video before. Light is shown at a prism. The prism then disperses all of the energies, and in white light, we see every one of the colors, and that's important. But we're going to do something different. What we're going to do is we're going to take a tube. We're going to evacuate everything out of it, and then we're going to fill in one element on the periodic table. Okay? We're going to put in a gas. Then what we're going to do is we're going to plug it up to a big electrical source, and we're going to give it a lot of electricity. So we're going to give that gas lots and lots of energy. Now, when we do that, okay, what we do is we talk about we're going to excite the atoms. Whew, they're excited. Okay, if I plugged you in, you would be excited too. Okay, you would get more energy in you than you once had. Too much energy might not be good for you. Okay, might do something to your hair. I don't know, but the electrons in the atom is where the energy is going to be absorbed. Not in the nucleus, it's going to be absorbed in the electrons. And so what I'm going to do is I'm going to take the electrons from their normal state, what we're going to call the ground state, okay? Normally where they like to be. And then we're going to excite them. Ooh. And now the electrons are excited. Okay, so I'm sitting, chilling in my ground state, and then I hit it with a lot of energy, and the electrons then become excited, and they're really excited, and then they have too much energy, and I'm really excited. And when you get excited, can you be excited forever? No, you can't be excited forever. Eventually, you're going to have to come back down to the ground state. So, what actually happens is, for a moment in a time, the electron will absorb energy, will take that energy in and become excited. Okay? That means the electron has more energy than it normally did. Then it's going to release that energy and go back down to its ground state or its normal state. Okay? And when it releases energy, it always releases energy based upon C equals lambda nu. Okay? I can calculate the energy. Okay? Energy is Planck's constant times the frequency. And so I can actually determine what kind of color the light comes off. Now, this is where it becomes oddball. When we take a look at light coming from, and in this case, sodium metal, what light do you see? Do you see all of the light? No. You see from sodium one single light, one specific wavelength. So how much energy is coming off of that sodium? What does that represent? How many energies? A single energy. So when I throw random electricity at the sodium atoms, all of them absorb. And all of their electrons get excited. And then all of those electrons can't be excited forever, so they transition back down to what's called the ground state, their normal state. Here's the deal. Every single energy that comes off of those sodiums is exactly the same. Okay? Now, sodium has 11 electrons. I can excite any of those electrons, and they can go up into higher energies, and then they can come back down. And if you have lots of them, if they were randomly distributed, then I would take an electron and kick it up, and it come back down, kick it up, coming back down, but the up and down would be, I'd start at different places, I'd go higher in different places, and I would expect that the transitions would represent every single transition between energies that I could ever possibly have. You would expect to see every single wavelength of light coming off of an excited atom. But in this case, I see one. That was shocking. Because we thought the electrons were just randomly distributed, just buzzing all around. Okay? But it doesn't seem that way. It seems that when every one of the sodiums in there gets electricity, the electrons can shift from one place down to one specific place, and only one energy come off of it. So that means the electrons, to give this outcome, must be in very defined spaces around the nucleus. Nothing that we absolutely ever imagined. So here is an example. This is a different element.
If a sample of hydrogen gas is heated, it gives off light. When you view this light through a prism, you'll see an emission spectrum consisting of bright lines at specific frequencies. Because the spectral lines come at definite intervals, this suggests that specific energy levels exist in the atom. A cross-section of an atom shows the energy levels similar to the rungs of a ladder. When energized, the electrons move temporarily to higher energy levels. As the electrons fall back to lower energy levels, they lose energy in the form of light, which produces the characteristic spectrum of the elements. Because we know that the emission spectrum for each element is different, we also know that the distances between energy levels must be different for every element.
Okay. Hydrogen had 4 lines that we could see. Other elements have different lines. Each one is specific and unique to every element, but the fact that the transitions were quantified or quantized, defined levels, that was an odd circumstance to us. We didn't really expect this. And this really then made us really think about, okay, where are these electrons actually in? Where are they located? Rutherford originally had the center nucleus and then all of these electrons buzzing around. But what he really thought about it in terms of his mind was that the electrons were orbiting the nucleus like the planets orbit the sun. Now, there was mathematically, that doesn't work. If you actually are in orbits, because we understand orbits around a mass, and every time you orbit something, you actually lose a little bit of energy. And so over time, if you lose little bits of energy, the orbits will decay, and if it decays, then all matter will be nothing, and that doesn't happen. And so his idea, although he found the volume was mainly empty and the nucleus was, excuse me, very tiny, he didn't have a great idea where the electrons were. This experiment by Bohr created, well, they must be in defined areas, and so just to be not confusing, he called each of his levels orbitals. They are not orbiting, but they are defined areas from the nucleus. Okay? And here is where we actually get energy. How in the world do the electrons actually have energy? What charge is an electron? Negative. You better know that for the test, right? What charge is the nucleus? Positive. So, the electron negative and the proton positive, what did we say about positive and the negatives? They attract. The closer I get a positive and a negative, the more stable it is, or I can give off energy. Okay? And so the electron being close to the nucleus gives off energy because they are stable, because they want to attract to each other. Okay? Now, an electron in quote-unquote higher energy is this. The nucleus is here, in the center, and if I move the electron away, the positive and negative is farther away from each other. There's not as much stabilization. That means this electron has to have more energy to live farther away from the nucleus. And each time I move farther away, the electron has more energy, and the electron has more energy, and the electron has more energy. Bohr's model defines what's called the principal quantum number, and electrons can live in levels of 1, the closest it can be to the nucleus, then the next level is 2, then the next level is 3, 4, 5, 6, 7. How far do the levels go out? Theoretically, it could be what? Forever. But here's the problem. Nucleus has positive charge, electron has negative charge. You get far enough away, they're so far they have no attraction to each other. That means the electron can fall out of the atom. Okay? So the more charge I have in the nucleus, the further my electrons can get away. The smaller positive charge, I can't keep them too far away or they'll fall off. Okay? And so there is a value. Now this value can actually be calculated. And take a look at the levels. Okay, they described it like a ladder. Okay, it is like a ladder. Look at the level 1, which is the closest to the nucleus, versus level 2. There's a little bit of distance between level 1 and 2, right? What about between 2 and 3? Much smaller, right? 3 and 4. They're not all equal. Do you see that? The charge and attraction really falls off quickly as you get further and further away from it. Okay? So what happens is those levels that are very far out get kind of close together. All right? The biggest stabilization, you can also talk about the lowest energy electron, is the ones that are closest to the nucleus. And what happened is when we excite them, we can excite them into any level. And they will transition back down. Each time energy is absorbed, I kick up or further away from the nucleus. Not the nucleus. Oh, yes, the nucleus, sorry. And then when I try to go to the ground state, I fall back down a level. Now, you can fall several levels at one time and give off energy, or you can fall one level and give off energies. Now, why did we only see a few energies? There are more energies that are given off when we excite these atoms, but there are only a few that end up in this small little range called the visible range. Some energies are X-rays, some energies are infrared. We wouldn't see those. They're happening, we just don't see them. It was kind of fortuitous that only a few came out in the visible range where we could see them, and they were not all over the place. This led us to calculating where these energy levels could be. Now, to actually find out the energy levels, we can calculate the energy of any one level using this particular equation. All right? It has something to do with how far away it is. And so here is how far away it is, the level. Then there's a constant number, well, a couple constant numbers. Do you remember this one? What do we call that one? Do you remember? It was in this equation, E equals h nu, Planck's constant. Do you remember what this is? C? The speed of light. Here's the new one, Rydberg constant. And that's a nasty number, okay? Now, some books articulate all three of these values, okay? But if you take this combination, and I use this one because this is easier to remember, all three of those multiplied together comes out to this number right here. That's what I use, the 2.18 times 10 to the minus 18 joules. And remember, if we're talking about energy, energy is in the form of joules. All right? And so 1 over, and the end values start at 1 and go up from there, all the way up to infinity, theoretically. And so you can calculate the energy of each level. The closest in would be 1 over 1 squared. So that's the full amount of energy that you can have for stabilization. But if you put in a value of, let's say, 1 to the, if you go to the 5th level, then you get 1/25th of the amount of stabilization as if you were right there, right next to it at level 1. So the further you go away, the less stabilization you have, or you can say it in another way, the electron has much, much more energy. If you actually put infinity down there, 1 over infinity squared is essentially 0, and you would have 0 energy. So you can get far enough away from the nucleus that you have no energy, and that means you're not attached to the atom anymore. Now, we talked about the energies that are coming off of these transitioning electrons that go from the excited state back down to the ground state. In chemistry, I have two equations on here. In chemistry, almost every equation is written in this form. The final thing that you do minus the initial thing that you do. So I like this equation because it has the electron in the final place minus where it begins. And we're going to do lots of calculations, and we do final minus initial. Okay? Now, if I use this equation to look at the change in energy that comes off when I go from one level to the next, I have to add a negative number to that, okay, for it to mathematically work out. And so I like this. The hardest part of that is remembering the negative sign. Some people use this one because you don't have to remember an extra negative sign, but this is the only time that you use initial minus final. Everything else is final minus initial, so I like the second one better. All right, when you do this calculation, you can end up with two numbers for energy. A positive energy number and a negative energy number. How do you have negative energy? That's not, you don't think about energy as being negative. I think energy is a value. The positive and the negative here is going to be the direction in which the energy flows. If the atom absorbs energy, it's a positive number. That happens when the electron starts at a low level and finishes at a high level. I have to absorb to excite that electron up. A negative energy comes from this. When an electron starts at a high level and goes to a low level, that electron has to emit or give off energy, and that energy could quite possibly be a visible light energy. Okay? It doesn't have to be in the visible light, but it does have to be energy coming off. And so that's what the positive and negative means for energy. It's the flow. Which direction? Is it going in or is it coming out? We're going to use that for all chemical reactions also. So if energy is coming into the system, I have to add it. And if it's coming off of the system, it is a negative. All right? So if we can look at this, then we could calculate what the energy values for transition should be. So let's try some of that. Now, I'm going to combine a couple things when we do this. This first problem is going to take an electron from one level to the next. Now, you can make an assumption, or you can actually evaluate this by just looking at the question before you even pull out an equation or even the calculator. Take a look at where the electrons are going. Where does the electron start in this question I asked you on the screen? Where does the electron start? What level? 4. And what level is it going to go to? 2. So is this going to absorb energy, or is this going to give off energy? Okay, so when you do your calculation, you should get a negative number. Okay? And you can look at that and have a check to see if you're heading in the right direction. All right. So when you do this, it says calculate the energy of the line in this is called the Balmer series that results from the transition from N4 to N2. And then it asks you a very specific question. What area of the spectrum is this? All right. Well, what area of the spectrum would be related to what color is it? And a color we normally look at and try to find out the wavelength. But before we have wavelength, we have to know the energy. And so we'll use the equation, and I gave it to you at the bottom of this sheet, to calculate the energy that, in this case, should be emitted from that transition. And so it is minus HC, Reiber's constant, parentheses, 1 over the value of the final squared minus 1 over the value of the initial squared. So first calculate that energy, and you're going to get a number, a value of energy. And then from that, you're going to transition to find what wavelength of light that is. value that we get is minus 409-ish e to the minus 19 joules. See that? Okay. All right, that's good. But that's not what the problem asked us. The problem asked us where on the spectrum it is. Okay. Well, I know this. E equals H nu, right? And so I can take this and that, and I can find nu if I take the energy I have and divide it by that constant. So, in this case, I don't use the negative sign. Why? What does that negative sign mean? It's just the direction it's being emitted. Okay. Now if I take joules, I will end up with a unit of 1/2, which is hertz, which is the value of nu. And if you actually do that calculation, you get this strange number, 6.17 e to the 26th. Nope, that was wrong. Six e to the 14th. Okay. That's still not really what I want. What I want is a wavelength, and I know that the speed of light is equal to the wavelength, which is all I want, times the frequency. Divide frequency on both sides, take the speed of light divided by what I just discovered, and I'll get a wavelength. So I take the speed of light, 3.00 e to the 8th meter divided by a second, and I divide it by that number I just calculated, 1/2.
Dr. D, I'm sorry. What does that say? It says mu 6.1726 e to the 14.
E to the 14th. Okay. And I get a value in meters. It comes up to this, 4.86 e to the minus 7 meters. Which, if I put it in nanometers, I'm not going to do the calculation, but you can change that into nanometers. 486 nanometers is the wavelength. All right. To get all of that, that's a long problem. Okay? The first problem, the first part of this problem is calculation of the energy. Normally, that's probably where I would have stopped in the first introduction of this kind of thing. But then I taught you how to relate. Oops. Stop. I taught you how to relate energy to frequency. So we got a frequency. And then I had already taught you the speed of light is the frequency times the wavelength, so we can solve for the wavelength. We get this number. There's the number. And if you take a look at 486 nanometers, look, visible light between 750 nanometers and 400 nanometers. 486 would be somewhere here-ish. So that would be bluish. Okay? And so you can calculate not only the energy transition, but also what its frequency and its wavelength is to get the color. And essentially, that is what they did when they saw all those colors was related back. Well, then what was the energy transition? How much energy does that really take? And this was the kind of working backwards to find out where those levels were for this to actually work out. It's a lot more complicated. There's a lot more calculations involved, but essentially, this is where we get this. Now, we now know it's quantified. We know that there are levels in which electrons actually live. There's another idea about light, and it's because light has both properties of a wavelength, like energy, and it has properties of a particle. And so what happens in light or energy is that it travels in two different ways. It travels like a light in waves, but there's also a particle there. And so there's a way to calculate how the wavelength versus for every particle that is moving. Now, most of the particles have almost no mass. So a lot of the things that we're talking about have very, very little mass. This is a constant that we already know. Velocity here, be careful. This is velocity. Where this one is in meters per second is this velocity. It is not new, the frequency. Mass is defined in kilograms. And H actually has units of a joule and a second. But a joule is a derived unit. A joule is really weird. A joule is really a kilogram times a meter squared divided by a second squared. That is what a joule is, times a second. That's what this right here means, is that. And so if I look at this equation, on the top, my unit is kilogram times a meter squared divided by a second squared times a second. On the bottom, I have kilogram, and on the bottom, times a velocity is meters per second. Now watch this. Kilograms cancel out. This second cancels out one of the seconds. This second cancels out the other second. This meter cancels out one of the meters, and what I'm left with is a meter as the unit, and remember, wavelength is in meters. So mathematically, all the units cancel out, but to do this problem, all of the masses have to be in kilograms, all the velocities have to be in meters per second squared, and then you have to use the constant number that we found. Now, in CHEM-111, are they going to give you meters per second? And are they going to give you kilograms? No, they'll tell you 4 pounds, that is going 100 miles per hour. And you got to figure it all out. Okay? Kind of like this one. If a person was traveling just like an energy wave, what did I just do? Okay. If a person was traveling just like an energy wave, and they weighed 75 kilograms, and they're walking at the speed of 2 kilometers per hour, what wavelength are you traveling at? Okay. First thing's kind of easy. You put in the constant, but at this point in time, what I'm going to do is I'm going to change the constant to make sure that I have the right units. And remember, these derived units, you can use them and you can change joule into this any moment in time. Okay, divided by the mass. Ah, good. We were nice. We at least gave you kilograms straight up. Times, and they said 2 kilometers per hour. So we must be walking in Canada. Okay. Now, kilometers we can't use. We need them in meters. And I always put the one with the one that has the prefix and the value with the base unit. So now I have meters that I can use. And remember, you've done this before. Hours can be converted into minutes. 1 hour is 60 minutes. And you've done this, minutes to seconds. And you know 1 minute has 60 seconds. And so hours are not there. Seconds, seconds are there. Because that's what we want. Minutes is what we don't have. And I've got meters over second, but then kilometers cancel out. One of those seconds cancel out. The other second cancels out. The meter cancels out, leaving 1 meter, which is what I want. And if you do that mathematically, you get something that is like this with lots of other numbers. But why do I not use that? Why do I only use a 2? Because that has 2 sig figs, that has 1 sig fig. And so you would go back to 1 sig fig to calculate the answer.